Now we'll continue with our notes on inscribed angles. So we'll do one more example with a inscribed triangle. And you can see here that one of the sides is a diameter. That automatically makes this a right triangle. Why? Well, this arc length is 180 degrees. Half of 180 is 90. So all I have to do is say 3w minus 9 equals 90 because that's a right angle. Then I add 9 to both sides, divide by 3, and I get w equals 33. You'll see a lot of triangles that are inscribed where one of the sides is a diameter because we love right triangles in geometry, because we can use Pythagorean theorem and do more complicated problems with them, more involved. So now here's an interesting thing. Can you actually classify a triangle just by knowing where the center of the circle is in relation to the triangle? So we're going to look at some cases where it's outside, where it's on the side of the triangle, and where it's inside of the triangle, and we will explore it with our GeoGebra. Okay, so here we have this application where you can move the centers of the circle and create different triangles. Right now, point A is in the center of the circle. Well, when we classify triangles, we want to look at the largest angle. So for example here, the largest angle is 76. Well, what's the subtended arc? That's the purple one, that's 153. And you can see the relationship is still holding. This is half of the arc. All right, now the point's in the center, so I'm going to make this angle bigger and bigger by getting closer and closer. All right, and now what's happening here? Aha, as I get, and it's very hard for me to get exactly on the diameter, but as I get closer and closer to 180 degrees, you'll see that this gets closer and closer to 90 degrees. Why is that? Well, when I get exactly, and I'm not going to manage it here, on this diameter, the arc that's intercepted will turn to 180 degrees. That will automatically make a right triangle. So when the center of the circle is on the side, it's a right triangle. When the center of the circle is on the inside, I'm not over 180 degrees yet because it's, so it's an acute triangle. What if the center of the circle is outside of the triangle? Well, now you can see that this is an obtuse triangle, and the arc that's subtended is actually more than 180 degrees. Well, if I have a number more than 180 degrees and I divide it by 2, the answer will be more than 90 degrees, which makes it obtuse. Now let's go ahead and take a look at this example where we're going to find each of the angles in a quadrilateral RSTU. So in this one, we're going to use the same relationship, but I need all my arc lengths, so let me go ahead and find this missing one. So I added all these up, plus ST has to equal 360. Combine like terms, solve for ST, and I get 42 degrees. Now, starting with angle U, I know that it subtends this arc right here. Well, that arc is 42 plus 46 degrees, or 88. Since U is inscribed, it's half of that 88. It's 44 degrees. Now I'm going to find angle T. That subtends, or intercepts, a much larger arc. It's this arc right here. It's a major arc, URS. So I have to add all these angles together, 46 and 208, divide by 2, and I get 127. For angle S, it also subtends a very large arc, 64 plus 208, divide by 2 because it's an inscribed angle, and I get 136. Last but not least, angle R is just 42 plus 64, divide by 2, and I get 53. Now take a quick look at the quadrilateral and look at angle T and R. These are two opposite angles. If you add those two, what do you get? You get 180 degrees. All right, let's take a look at angle U and S. When you add those two, what do you get? You also get 180 degrees. I wonder if this is true for all inscribed quadrilaterals or just this example if we just looked out. Well, let's go ahead and explore at GeoGebra 2 and see if that always holds. Now we're looking at quadrilaterals inscribed inside of a circle. So I've got these 4 points and I can move them anywhere on the circle. And looking at these opposite angles here, 101 and 79, what does that add to? It's 180. And I can move this point here. Notice that the point kind of stays the same here. This angle's not changing because the arc that's subtended stays the same. So this is 113 and 67. What does that add up to? It adds to 180. So it doesn't matter where I put the points. It will always add up to 180. Why is that? Well, right here, for this angle, let's say we take the blue angle. The arc that's intercepted covers this part of the circle. And we could figure out, oh, it's about 222 degrees, roughly. All right. The red angle, the arc that it intercepts, covers this part of the circle. This part right here on the blue side. Okay, and I could figure out, okay, double that up. That's about 68. Doubling that, it should be, if that's 222, and this is 68, I'm having them at 130, it's really close to 69. It's like 138. 222 plus 138 is 360. Why is that? Because we covered the whole circle between both angles. The red angle covered this part, the blue angle covered that part. So when I add the two pieces, they will add up to 360. When you have to divide 360 by 2, what do you get? 180. So both of these angles have to add up to 180 degrees, and they will always be supplementary. So based on what we found out, we can say that for any quadrilateral inscribed in a circle, the opposite angles in the quadrilateral are always supplementary. And that's because one's going to do one part of the circle, the other one's going to do the other part of the circle. Together, they do the whole circle, which is 360. 360 divided by 2 is 180. So they have to add up to 180. That makes them supplementary. So in this last example, we're going to solve for x in the quadrilateral at right. We're going to use the fact that those two angles are supplementary. So you don't know if they're congruent, but we do know they add up to 180. Combine like terms, add 3 to both sides, divide by 9, and I get a kind of a repeating decimal here, 20.3 bar, or 20 1/3. So in reflection, how can you use the center of a circle to classify and inscribe triangles as acute, obtuse, or right, even if the angles are not marked? What relationship did you notice between opposite angles in a quadrilateral inscribed in a circle? Hopefully you saw those angles are always supplementary. And then generally for a whole lesson, what relationship is between an inscribed angle and its intercepted arc, and how can we prove it?